All right, gentlemen. You saw that I posted another homework set for you, then the penultimate homework set, as I said. And you got 4 problems. It's a little beefier than last week's assignment. So, was that thanks? A heartfelt and hearty thanks? Yeah. Well, one thing that actually, let's just go to the homework just so I can highlight things that I think will be useful to you in preparing. This first one, something we've done a number of times, just making sure we have the good practice on finding the eigenvalues, the eigenvectors, and then the unitary matrix that will normalize it. And do you remember how to make the unitary matrix? Well, you can look it up, but it's just to make sure it's real simple. The unitary matrix is just the eigenvectors put together into a matrix. So if you have the normalized eigenvectors, you put them together. Make sure that you have it in the right order as which one's the inverse. The inverse is just done by taking the complex conjugate of the transpose, I believe. I say this off the top of my head because I have to look at it to be sure. So just test to make sure that your matrix does indeed work for diagonalizing it. The second one, an electron in the ground state of tritium, for which the nucleus consists of a proton and 2 neutrons. Just want to make sure you know you have three particles in the nucleus of tritium and 3 particles in the nucleus of helium-3. Thus, the masses are virtually identical, so you don't need to worry about the difference in the mass of the nucleus. For both of them, you have the eigenstate 100 is this function where the A0 is going to be, well, it's going to be the same for the 2. Yeah, I think A0 didn't have zenith, did it? I don't think it did. Just make sure if I'm wrong about it having zenith, but I think it doesn't have zenith. So the difference in the 2 is going to be that value. And what you're doing then is finding what the probability is of the 100 tritium after it becomes a helium-3 to be in the 100 state. So I'm not going to go through how to solve it, but just making sure you understand what we're doing here. Now, the next one is the one that I really want to make sure I touch bases on. Consider a molecule of Cn. That's a flat molecule. We're going to define this as having the z-axis whoops, wrong. We're going to define this as having the z-axis like this. So it can't have any angular momentum about that axis because the C and N are both on the axis. And so all of your angular momentum will be in the x and y directions. And then it says to write down the Hamiltonian that describes the motion. Tell me about the Hamiltonian. What is the Hamiltonian?
So it's the sum of the kinetic and potential energy as an operator. It's an operator that returns the value of energy.
Okay, that's great. Yeah, it's going to return that when it operates on the wave function. Well, for this case here, we're treating it as a rigid bar. It may be described by a dumbbell. And so if we're describing it as a dumbbell, we're going to say that potential energy is 0. So that's going to make your life a lot easier. Potential energy is 0. So then we have kinetic energy. What's the kinetic energy if I have something that's just rotating? I'm teaching general physics, so I use KE for kinetic energy. If I have something that's translating, what would it be? Translating is traveling a straight line. What's kinetic energy then?
So it's just the energy in x direction, or the 1/2 mv squared.
Right, 1/2 mv squared. Or rewriting in terms of momentum, p squared over 2m. And so that's what we've been using for the Hamiltonian before. But now we're just talking about rotational energy only. And so if it's rotational, what's your rotational kinetic energy? The equivalent to p squared over 2m.
I don't know about the p squared over 2m, but isn't it like 1/2 I omega squared or something?
Yes. 1/2 I omega squared. But L is equal to I omega. So how can we put that in terms of L?
So then L squared over 2 omega.
Close.
It'd be L over 2i.
Yeah. L squared over 2i. So then from this, you should be able to make your Hamiltonian. And just tell me, so I don't want to be like I gave them the answer, but what is the Hamiltonian going to be then?
L squared. Yes.
Yeah, it wasn't very different, was it? I just changed it from L squared to L squared operator. That's why we put it in terms of L. So that's my Hamiltonian. So my solutions, what can you tell me about my solution eigenstates?
Did you mean to make that L squared not L?
Yes, I did.
2 for LC?
Yes, I did. What do we call the eigenstates of L squared? The angular momentum is L, but the eigenstates of L squared. It's something we've been focusing on of late.
So does it have to do with the momentum in the z direction?
Well, angular momentum inherently is going to have something to do with the angular momentum in the z direction.
Right.
Anything that has potential energy that doesn't depend on the radius and is spherically symmetric is going to have the spherical harmonics.
I see.
So your eigenstates are going to be the spherical harmonics.
When you say in that first line of blue, is that supposed to be so eigenstates and eigenstates?
Yes.
Or is that
The eigenstates of the Hamiltonian are eigenstates of L squared because the Hamiltonian is L squared times a constant.
right?
I mean, it's a redundant statement, but it's an important one because that tells you where your answers are.
Right.
And so from there, you should be able to do the rest of it. And then the last one just has finding the probability of LX, well, yeah, LX if it's in same L state but different M1 and M2. And it says to use ladder operators so you know that L plus minus is equal to LX plus or minus ILY. And so you write LX in terms of the ladder operators and LY in terms of the ladder operators, put them in there, and you find an interesting solution.
Sweet.
By interesting, I mean it's not the trivial solution, but it's also not super grotesque. Okay, My title, I'm not going to talk about bonding and anti-bonding states today, so I hand wrote a title after I realized I actually had changed the name of the file, but didn't change the name of the title slide. So, picking up where we left off on Friday. The preceding work. Oh, good. I did not notice that I had the preceding work on Friday showed us that when we combined the two spin 1/2 particles, we could get two different total spin states. One if they are aligned together, of spin is 1, and one if they're anti-aligned, of spin is 0. You can't have a negative total spin state. It's either 0 or 1. And if you're in a spin state of 1, then the orientation can be anywhere between 1 and -1. If it's 0, the orientation is 0. So we had the triplet states if it was a total spin of 1 and the singlet a total spin of 0. And I don't know if I mentioned this, when I was in college physics, quantum mechanics, I never understood what a singlet or triplet state was. So hopefully at least I can give you that I didn't get when I was taking this class. So it's a general rule, when you combine two different particles, you can have the spin state anywhere between the maximum and minimum you get with adding them. So if I have 3/2 and 2, what's the maximum alignment I could get if they're totally aligned?
So 2.5.
Well, 2 plus 3.5 is actually 3.5, or as we'd prefer to say, 7/2.
Same thing.
All right then, that's the way we're doing math. What's the minimum we could get?
So we would do 1 minus 2, right? So the 1/2 minus the 2, so that would be the negative 1/2.
Can't be negative, so that's not it.
So then 1/2.
It is 1/2.
Yes, 1 minus S2. Why did the God is
That-
that's values.
Doggone it. I wanted that to be in a different color. I worked so hard, and then I changed back to fix the other one. That's not the same color. That's the same color. Okay, so I did the absolute value of the difference. So the spin can be 7/2 to 1/2. Are there any spin states in between those that it could have?
Yes.
How much could it shift by?
By integers.
By integers. So that means that this could go from 7.5 to 5.5 to 3.5 to, I keep saying ands. 7/2, 5/2, 3/2 to 1/2. We could have S as all of these. And then what about our M sub S values? If it has a spin of 7/2, what's the M sub S values available to it?
So the plus or minus S, right? So all the way to minus to plus. Yeah.
Right. So there's lots of options for the 7/2, 2 less for 5/2, 2 less for 3/2, and only the 2 value. Oh, I put 0 in the middle. There is no 0 in the middle here. There is there. Right, if you're changing by 1 and you're 1/2, you don't get 0.
Right.
Fact. There, now it's complete. Okay, so those are, in general, the states you can get if you combine the two particles. Now, let's take a specific case here, and these are perfectly distinguishable. In a hydrogen atom, you have a proton and an electron. And you can differentiate the proton from the electron. So these are distinguishable. That's actually an important thing here. And so the proton has a spin of 1/2 and the electron has a spin of 1/2. So what is the total angular momentum I can get in this case? Actually, let's answer the second one first. What's the total spin I can get? It can be 1 or it can be 0. That is, it can be 1/2 plus 1/2 equals 1, or absolute value of 1/2 minus 1/2 equals 0, and any integer in between, which don't exist. So we can have those two possible spins. What about the total angular momentum? Notice a new symbol. It has angular momentum state L, and I want the total angular momentum J. So J is equal to total angular momentum.
Total angular momentum is square root of L times L plus 1. Is that how it works?
Yes, but I'm looking for the quantum number. You're correct. But I was looking for the quantum number, not the actual value there. So how do I find the quantum number J? I'll put it at the lowercase j. That's what I should have done.
Let's say S squared.
It turns out the same rule that we have for the spins will apply for the angular momentum. So J could be anywhere between L plus S total to absolute value of L minus S total. So I have two options now because I had S total of 1 and S total of 0. And so I could have L plus 1 or L plus 0 as the maximum, depending on the S state. Or I could have absolute value of L minus 1 for the other. So we have different potential values for the spin state depending on if it's in the singlet or the triplet state. Yeah. Does that make sense to you as far as how they add?
Okay, so I have two questions.
Yes.
When you say distinguishable between the protons and the
Electrons. Yeah.
Does that mean distinguishable spin? Or like you can just tell how many protons and electrons there are?
You can say this is the proton, this is the electron.
Okay.
As opposed to if I have a helium atom with 2 electrons, I can't say this is electron A and this is electron B. There is no way to tell one electron from the other. So that's indistinguishable, which is actually coming up in about 2 slides. That's why distinguishable is really important.
Question.
Huh?
We're talking about the singular state and the triplet state. Those
Mm-hmm.
are them that are. Okay. I just answered my question. Yeah, that's right. Okay. Makes sense.
Okay. The total spin state for the hydrogen atom, which is what we just did, will be a superposition state of the different ways that the total S and M can be achieved. So looking at what we just did, let's say it's in the triplet state. It's in the S equals 1, and then we could have M equals, let's go with M equals 0. S equals 1, M equals 0. We actually already did kind of that problem. We did it with 2 electrons and did it that way. And the way we do it to make our lives easy is to look at a table that other people have already done all of the work for us. So we have the SM state, the superposition state of all of the different combinations that give us, in this case, our triplet state with M equals 0. is found by using these Clebsch-Gordon. I think that's how you spell Clebsch. And Gordon only has two ways, so I'm 50-50 on Gordon. Clebsch-Gordon coefficients. Our textbook has a Clebsch-Gordon coefficient page, but it's missing an important key for reading it. So here is basically the same thing, but with the key. There's the key, how to read it. So what we just did was 1/2 by 1/2. This is the problem we just did because we had two spin 1/2 particles that we put together. And so we read those, and this here would tell us a combination of J and M, which in our case, because we're just doing spin, would be S and M. And so we look here, and I just said of 1, 0. So there's 1, 0. Here are my options. Okay, change the color. Here are my options for the, these are my options for the particle. Spin 1/2 and spin minus 1/2. And so this is going to be, I did this before class. For the two particles, it's going to be, we're looking at these, and then finally, we have these for the coefficients. So, yeah. I should have. Actually, is this the same as what our table is? Does it have a minus on both lines in our table in the book?
Yep. No, it has a plus minus plus. So that's right.
What page is it in our textbook?
188.
188. Okay. I just want to make sure this is the same because suddenly it's like, is that really correct? Oh, like I can read that. Yeah, it's the same. Okay. So the way you read this is you say that that would have turned out wonderfully. 1, 0 for our case here. So we got that from reading the yellow highlight is equal to, and then you take the coefficient that's here. I just unerased it. It was in green. And that's going to be square rooted by default. So square root of 1/2, and then I have 1/2 minus 1/2. Yeah, this is correct now that I think about it. And then I have plus. And again, it was 1/2 with the implied square root. And then the next one is minus 1/2, 1/2. Or as we would more normally write, since they both have 1 over square root of 2, that's up, down, plus down, up. So that's how you read it. So the things in blue, well, I'll just highlight to match. There's the things in blue. And the things that are currently uncolored, I will color them in orange. Those are this and this. And of course, the yellow, final one, was this here. So that's how you read them. So we're going to come back to this in just a moment to do another example where I want you guys to read the table and tell me what my eigenstate is going to be. So going to here. Wait, didn't I swear I put 3/2.
Might have put it down in the slides.
Or I might have deleted it because I'm pretty sure it's not there. Darn it. Well, didn't I do the math adding 3/2? I did the math, but yeah, wow. Yeah, not there. So let's just do it. Let's say we had a 2. Okay, if S, make sure we have that set here. That's 2 3/2. Nope, I don't have that. Okay, I'm going to do this one. I'm going to do 3/2 by 1. So I have 1 is 1, 1 is 3/2. And I say, what is the state? Well, let's go from here. What possible values for S total can I have? Okay, so I can have those 3. So I'm going to go ahead and just select one of them. I'll select this one. What values can M sub S have? Okay, so how would you term this state? How would you term this? We had singlet states and triplet states here for the spin is equal to 1 or 0. What would this be? It'd be a quadruplet state. And now let's choose a specific variation on this. Well, we can look here at our table and see this table has a lot of options. 5/2 for the spin, 3/2 for the spin, 1/2 for the spin. You also have, that's all you have for the spin. And then for the orientation, you have orientations of plus 5/2, 3/2, 1/2, minus 1/2, and so on. So we've got a lot of different options in the table because we have all the different variations. So let's just choose one. Just choose which one we want to do here for the M sub S. Negative 1/2? Okay, so what we're going to say is, what is the state for a spin of 3/2 and orientation M sub S is minus 1/2 for our case? So what's the first thing I'm going to do with those numbers? Find them. Okay, let's do that. Let's find them. So we have 3/2 and minus 1/2. Can you find it?
Middle, and like
1, 2, 3. Okay, so notice we have 3 possible states there that we're going to be combining. So what do I have for my State.
So then it'll be 8/15 one square root of 8/15.
That's right. That's right.
And then we have 1/2 -1.
Minus. Good. You read that. It's assumed. Okay, you have the assumed square root, but the minus sign is outside of the square root. Yeah.
Okay, that's all I thought. That's what I thought you were going to minus square root 1/15. And
Negative 1/2, 0.
And then minus 2/5, or square root 2/5. Negative 3/2 and 1.
Okay. Not so simple, is it? It's easy to read, but obviously these things are complicated. So learning how to use these Clebsch-Gordon coefficients makes life easier. And you notice that your table does say, it does, oh, come on. I forget when I have a highlighter and when I don't. Your table has this line, although it doesn't have the example. It just doesn't have the table on how to read it. And it's really hard to figure out how to read it if you don't know what's supposed to be where. So, not for your assignment today, but for your final homework assignment, I'll probably give you something where you have to use some Clebsch-Gordon coefficients to get a little practice with it. You've shown that you have the mastery.
All right, just to walk through one more time. For our J and our M,
Yes.
how did we get those in?
Okay, so that came from how can I add them? Okay, so that came from how can I add the spins? If I have two particles, and if you have three particles, you can always add two, find all the options for those, and then take the third one and add it to each one of those options, and that gives you your full yay. Obviously, it's a lot of work. But you get them from adding. So I had, in this case, I started with 1 and 3/2. With 1 and 3/2. And so that told me which table I was looking at. And then once I know which table, I say now if I add these, my total spin can be anywhere between 1 plus 3/2 to absolute value of 1 minus 3/2. So that's how I got the three options for S. And then for each option of S, I could have between M sub S is between plus S and minus S. And so I chose 1S and found the M sub S values. And then we said, okay, now that we have that, which states would give that to us? We didn't even have to go back and figure out which states would give it to us because it was in the Clebsch-Gordon coefficients. These are the three states that gave us that.
And I also have a question. So the J notation here.
Yes.
What's the difference between that J notation and our S notation here?
Okay, so that's a good thing to get straight because I kind of introduced it here, right? This is the first time we saw it. And so that color's bad. J is equal to total angular momentum. L is equal to orbital angular momentum. S is equal to the spin angular momentum.
Okay.
So J, and doesn't work in that. J is equal to L plus S following the rules of adding spin. So that means it could be anywhere from L plus N to absolute value of L minus N. or S, L minus S. I don't know where N came into my vocabulary, my vernacular. So that's what J is.
So whenever they say J down in the table, they just assume you're going to use either L or S? Or?
L or S or J. It depends on your problem, on what specifically you're doing. So J is total angular momentum. It could be the total orbital if you only are working with orbital. It could be the total spin if you're only working with spin. And so, yes. Yeah, but it's the total. And then the M is the magnetic, so it's the orientation.
Right.
Yeah, so the capital M is the orientation for the total, and the lowercase m's are the individual. That was distinguishable particles. Now we're going to go to identical particles. So now we're saying like, oh, let's suppose we have 2 electrons in an atom. So I have a helium nucleus with 2 electrons orbiting it as an example. If I have a helium nucleus with 2 electrons orbiting it, I can't distinguish those 2 electrons. I just have 2 electrons. And one electron I will label with R1 and one with R2, the radius to 1 and the radius to 2, but I can't tell the difference in which one's 1 and 2. So if I am looking for the Hamiltonian, my Hamiltonian now has, if it's a subscript of 1, it means I'm doing the del squared with respect to radius 1. If it has a subscript of 2, I'm doing del squared with respect to radius 2. And then I have the potential energy, which is a function of both the radius 1 and radius 2. That's very, very general. That works for any problem so far. It's also fairly useless because it's going to take a lot of work. So let's get ourselves specific to an atom with 2 electrons. If we have 2 electrons, all that's going to matter is the separation between the 2 electrons. Right? Nobody cares about where they are. We care about how far apart they are because potential energy depends on their separation. And we're going to introduce a new thing that we call the reduced mass. The reduced mass is the effective mass you get for the center mass problem. And obviously, you don't start by defining the reduced mass and then working through the problem. You work through the problem and find, oh, my life would have been easier if I'd made this substitution at the beginning. Right? So it's just like when we said, or the textbook said, for reasons we will only make sense later, I'm going to say this is equal to L times L plus 1. Right? That made no sense. But at the end of the problem, you're like, wow, it would have been a lot easier if. Yeah. So that's where the reduced mass appears for us here. So now I can rewrite a couple things. R, this R here is the separation and this R here is the position of the center of mass. So we're not getting rid of a variable. We're introducing 2 new variables, well 3, but one's a constant, the new constant mu. 2 new variables, lowercase r for the separation and capital R for the position of the center mass. So R1 and R2 are going to be replaced with lowercase r and capital R. Same number of variables, but it's going to make our math easier. So we define the position of the center of mass very simply. Mass 1 times radius 1 plus mass 2 times radius 2, all divided by the total mass. And so this is where the reduced mass actually comes from if we do the calculation. This is expanding out the right-hand side of the equation, the one that has reduced mass in it, just so we can see that it comes to be the same thing. Or see if I made a mistake. I mean, it's always an option. It's an option that all too often is true. So now if you look at it, we have M1 times R1, M1 times R1, divided by M1 plus M2, divided by M1 plus M2, and M2 times R2 divided by M1 plus M2. So yes, indeed, they're the same thing. So what was the point of doing this? The point of using the reduced mass was to make this simpler. So how is that going to make life easier if it looks just a little bit simpler? If we rewrite the Schrodinger equation, now here's something I didn't do and I'm not going to do. We had before del squared 1, which is equal to, in Cartesian coordinates, I didn't hear what you said, Chris. Really? To me,
in electrodynamics, every time we change to spherical coordinates for polar stuff, it makes the entire problem so much easier. So
well, yes.
Yes,
it makes the problem easier, and that's why we do it. But for writing del, it's easier to do it in Cartesian. So that was del 1 squared, right? So the 1 was derivative with respect to x1, derivative with respect to y1. And so we had del 1 squared and del 2 squared. Now we're going to have like this, right? So I use Rx and Ry just to indicate it's the X. I guess I could have put it like this. That's what I did before. So it's the X, Y, and Z coordinates for capital R, and likewise for lowercase r. Like I said, not gonna, because it would take the rest of the class period and then some. But if you convert using these definitions for capital R and lowercase r, the Schrodinger equation becomes, there is the, what was one term, h bar squared over 2m del squared, 1, and h bar squared over 2m del squared 2, becomes these two things. And the potential energy function is only a function of the separation. Now there's the advantage that was gained. The advantage that was gained is that our potential energy is only a function of one of the two r variables. So I can take this equation that I'm highlighting the whole darn thing, and I can break it up into two different equations. I can take everything that has a capital R. So what has a capital R? This has capital R. And assumedly, the total energy is the energy associated with capital R plus the total energy associated with lowercase r. Because it's just a scalar value, I can just say it's the sum of these two. And so I took out part of this energy to give me the equation that will be highlighted in blue. So this is the capital R equation. And then the lowercase r equation is going to be highlighted here in green, maybe. And you have the potential energy in the lowercase r equation. Now, inherent to this, but not written, was the, well, psi is psi capital R times psi lowercase r. Right? If you don't do that, you can't separate it. But now we've separated into two separate equations. One equation is actually simple. Which of these two equations is simple, gentlemen? This one, because the potential energy doesn't exist in that equation. It doesn't have it. So we just have del squared of this thing is equal to a constant times psi. That one's not hard to find the solution for. And then this other one is actually the problem that we've already found the solution for. We've already found the solution for potential energy is 1 over r squared. And so this one we've already done the solution for. And the one above was fairly simple. Yeah, go right past that. Back to how we combine the solutions if they were distinguishable. If they were distinguishable, you just had psi A times psi B and you were done with it. But if they're indistinguishable, you have a problem. So if they're indistinguishable, you're going to have to say, well, it could be that the first one is psi A and the second one's psi B, or it could be that the first one's psi B and the second one's psi A. I can't tell the difference. And so you're going to have a linear combination of the two. Now, the 1 over square root 2 is simple for normalization. But you have two solutions, a symmetric and an anti-symmetric solution. So symmetric will have the plus sign. Anti-symmetric will have the minus sign. But you have two different solutions. And those two different solutions are going to behave differently. So we have the distinction of bosons versus fermions. The plus sign, and of course, did I say that was that symmetric or anti-symmetric for the plus sign?
Symmetric.
So the symmetric solution are what we call bosons. We call them bosons because Satyendra Bose was the person who did the work to describe how these wave functions will operate. Now, as I understand the history, Satyendra Bose did the work, and then he sent his calculations to Albert Einstein and said, does this look right? And Albert Einstein said, by golly, it does. And so they're called Bose-Einstein particles because both of them collaborated on this, but the primary person was Bose, as I understand it. He used Einstein as a sounding board, to make sure, did I make a mistake? Now, if you have the minus sign is the anti-symmetric. And those are named after Enrico Fermi. Now, I don't know about the sharing of work between Fermi and Dirac, but those are the anti-symmetric. Solution. And we will end with one important distinction about the difference between bosons and fermions. With fermions, if I have both particles in the same state, let's say psi sub A is the same as psi sub B because they're both in the same state. That is, they both have the same, if we're talking electrons in a helium atom, they both have the same N, L, M sub L, and M sub S. So if psi A is equal to psi B, what do you get for this superposition function? You get 0. So you cannot have a fermion, a particle with the anti-symmetric solution, with both particles in exactly the same state. Hence the Pauli exclusion principle. The Pauli exclusion principle is the simple statement of the result of, of the Fermi-Dirac calculations that say that if you have a fermion, if you have the antisymmetric solution, there is no solution for the two particles being in the same state. Now, what makes a particle a fermion? If it has a half integer spin, it's going to have the antisymmetric solution. So particles with half integer spins, whether it's a proton, a neutron, or an electron, all have to obey this Pauli exclusion principle. Bosons, on the other hand, with the symmetric, if psi A is equal to psi B, no problem. Right? If they're in exactly the same state, it's no problem. So they have no Pauli exclusion principle if they're bosons. So photons with a spin of 1, they can all be in the same state. But electrons with a spin of 1/2, they all have to be in different states if they're indistinguishable. That ends our time. Questions?
What's a meson?
A meson? Mesons are, they're intermediate weight mesoparticles. Mesons, it actually turns out, are quark anti-quark pairs. So for instance, you know, a proton is an up, down. It's 2 up quarks and a down quark. A neutron is an up, down, 1 up and 2 downs. Well, a meson, and I don't know which meson I'm going to do here, so I'm just making one up, might be an up anti-down. That's it. It's a different type of proton, or particle, excuse me. So mesons are intermediate in mass because they have one less quark than the baryons, which are the heavy particles. Protons and neutrons are baryons. And then you have leptons, are a completely different category. Leptons are electrons, muons, and taus. Leptons are light particles. The ones that are made of quarks are combined into a category called hadrons. Hadrons are particles that interact via the strong nuclear force. Quarks do. There you have it.
Cool.
And I will guarantee you that Blake knows far more about this than I do.
Yeah, in our lab, there's a big poster on the wall that has like all the classifications for leptons, baryons,
Yeah.
all that kind of stuff. It's pretty interesting.
All right, I'll see you guys. Will you be there tomorrow for tutoring?
I'll try.
Okay.